Uppu Srinivas Rao. He has joined. So today we are fortunate to have Professor Rao as our eminent speaker. So I'd like to introduce our speaker on this juncture. Professor Rao is a BTech from NIT Rourkela. He has done his masters MTech from IIT Madras and a PhD from IIT Madras in 2013. So he has been working as an engineer in Hindustan Motors Limited, and then he joined JITM Palakhemdu, Odisha, and then Vilamalal Engineering College, Chennai, and finally he joined BHU, IIT BHU in 2018, and since then he is working.
No, I am here from 2004. Actually, that 2018 I became associate professor there.
Okay, okay, okay. So you joined. So Professor Rao joined in 2004 at IIT BHU, and now he's an associate professor at IIT BHU. His current interest area includes micro machining, machining of composite materials, manufacturing tribology, tool conditioning monitoring, modeling and simulation of machining. He has several sponsored projects from Bark and other organizations like BRNS. He has been awarded national scholarship in the year 1998 uh, on the marks obtained in HSC Odisha. Now he is a life member of Indian Society of Technical Education, and he is also a fellow of Institute of Engineers India. He has guided several PhD and as a supervisor, and also as masters supervisor in MTech. He has also a number of international journals as well as international conference proceedings. So Professor Rao is an eminent personality in the field of micro machining. So I hope today's session will be equally interesting. So Professor Rao, the stage is yours.
Thank you, Professor Bose, for that nice introduction. Okay. Actually, Professor Bose and myself started long back our
Yes,
career together at Hindustan
together.
Motors.
We are friends.
And,
We
and
are old
we
buddies,
are
old friends.
still having that good relationship.
Yes,
Thank you, Professor Bose, for inviting me for this lecture.
always for my
Okay.
friend, always for a friend.
Okay, thank you. And I work, as he has mentioned, I work in the area of micro machining. So, and micro machining and machining. So, and the different allied areas. And with that in mind, and the theme of the short term course of this program, so I will be delivering a lecture on ductile regime machining of a specific material, that is bioglass. So let me share my screen and the PPT, then we can start the lecture. Am I clearly audible? Can
Loud and
anybody?
clear. Loud and clear.
Okay, thank you. Thank you.
Yes, sir. Your screen is visible.
Okay. Hmm. Okay, screen is visible, so slide changing is happening.
Yes, 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 sir. Absolutely perfect.
Hmm, okay, okay. So let me introduce the topic. So we are going to discuss about ductile regime machining, actually, which is very closely associated to micro machining. Micro machining and ductile regime machining, the main commonality is very low depth of cuts and low feeds. Okay. At the same time, the spindle RPMs will be very high because the cutting tools are small. Of course, that is the common area, but ductile regime machining can be in terms of macro machining as well. It may be similar to normal milling or any other macro machining process. Okay. So, as the name indicates, when we say ductile regime machining, we naturally say that it is machining of brittle materials, because otherwise there is no question or no point in machining a ductile material in ductile regime. Ductile material will always be machined in ductile regime only. Now, there are certain challenges in machining brittle materials, and as a example, we have taken 45S5 bioglass. Uh, However, the findings can be generalized for other ceramic materials which are normally brittle materials. Okay. So basically what we are discussing is ductile regime machining of brittle materials. So in this I will go as per these points bulleted shown here: introduction, traditional methods, recent developments, and what is the research focus in this area now, and what efforts we are putting at IIT BHU, and some I will summarize the talk and references. We'll have some break in between at around 8:10. Now, to start with, sometimes I think I want to see the participants. Okay. Now, there may be many teachers in the audience and who might be dealing with metal cutting or machining. And in all these things, what we have is metal cutting takes place. Metal cutting is basically systematically removing material layer by layer by engaging a hard cutting tool and providing relative motion between the workpiece and the cutting tool. This is how the machining happens. Okay. And in that, there are two basic mechanisms which are involved. This is the basics of machining. Okay. One is deformation and shear that happens for ductile materials. So in that process, we have yielding before the cutting tool, and then we have brittle fracture. That mechanism is basically for brittle materials. Okay. So in case of ductile materials, at just in front of the tool tip, material gradually gets stressed, and then when the stress developed is more than the yield point, then yielding takes place and there is a crack generation happens, and it propagates and slip takes place. That takes place resulting in the shear deformation of the plane of maximum stress. So this is where we have the shear plane and shear angle. Then in case of brittle materials, so what happens? The this is the this diagram shows, so material gradual crack gets initiated, and gradually there is the crack propagates and it gets separated. Okay, and this process of separation, swelling, further swelling and separation, so this goes on repeatedly. Okay, and in this process what we get is the chips are very small or discontinuous chips. So this is the way brittle materials are machined. So we have a crack gets initiated before the tool tip, and gradually that crack propagates and we get the material removed in terms of chip. Then what is the problem with that? In this problem, when the discontinuous chips are forming, so it during breaking there is a vibration generated, so it may give rise to very rough surface. Okay, and another issue is that because these materials are very hard, we need always very still harder tool materials. Now, what extent we can go for harder tool materials? So, affording tool materials to satisfy the requirements of cutting of brittle materials, that means we need to have tool materials which can satisfy this high cutting temperature. So we need a very high hot hardness and hot strength. Okay. Then apart from this, it should withstand the thermal shocks, and there should not be any built up edge formation when we go for lower velocities in order to control the cutting temperature. So to have this restricted rapid tool wear and reduced tool life, this has to be restricted. We need to go for high end cutting tools, maybe CBN or diamond, which is not always economically viable. Okay, so we cannot go for everything, we cannot go for these cutting tools, and in some cases, in case of ceramics, they themselves are very hard. Their hardness is comparable to normal cutting tools, like say tungsten carbide, cobalt, etc. Cemented carbides. So with that kind of hardness, we may not afford to cut at all using these traditional processes. So normally what is done is, normally we have to choose certain cutting tools, then a certain cutting process, okay, to have the material removal successfully. So before going into that, another fundamental aspect I want to share with you. These are all textbook material. This is not very new thing, but long back these are compiled. So what are the possible ways to improving machinability of work materials? One is we can change favorably the composition, microstructure and mechanical properties by certain amounts of additives or heat treatment. Normally through heat treatment such as annealing, etc., we try to soften the material so that the cutting process can be easier, or we try to add certain additives on the surface of the material so that the material removal becomes easier. Then another proper selection and use of cutting tool material and cutting tool geometry. This is the vast amount of machinability research where we optimize speed and depth of cut for any combination of workpiece and tool. So we do this. In that process, we choose optimum selection of these things and then cutting tool material and cutting tool geometry. So all of you know that cutting tool geometry is specified by 6 angles and nose radius. So all these parameters affect the cutting in different ways. So optimizing these angles and nose radius, speed, field, depth of cut, this is one way to optimize the cutting process. Then some more method is appropriate method of application of cutting fluid. In this actually we choose a right cutting fluid. In some cases, suppose machining of titanium with cemented carbide. If you go for dry cutting, the tool gets worn out very quickly. But if you use certain cutting fluids, the tool life gets increased. Okay. So this is another way. So when we say application of cutting fluid, that includes choosing a cutting fluid, then applying that in different ways suitably. There are many ways have been devised for application of cutting fluid. So we know, and these things are continuously getting improved. Then proper selection and application of some special techniques. So this is a ever increasing methodology, or this gives innovative ideas. So in that some are already established in the sense we can use these things in different ways to different applications, like dynamic machining. So we use certain kinds of vibrations. So when we say vibrations, we can vary the wavelengths and frequencies of the vibrations applied, and then whether continuous or pulsing, some changes can be implemented in that. Then hot machining. So hot machining and also known as in some cases hard machining, high speed machining. So these are all related. Then cryogenic machining, another reverse effect. Instead of increasing the temperature, in many cases, if we can reduce the temperatures, then the material behavior changes. And but in all these cases, it should be taken care whether that process is economically viable or eco-friendly or not. So these two slides actually in this gives whole gamut of many new things which are being adopted in different situations of machining are part of this. Through this we can go for newer things. Okay. With some small variations to that. Now, in case of, so from this discussion, what we can summarize is for the main issues with brittle materials are it is having high hardness and brittleness, so we need more costly tools and processes, and it gives rise to discontinuous chips which may lead to poor surface finish. And if we select these things, then it will give rise to low material removal rates, but through this the process is feasible. So there is always a tendency to have low depth of cut and low feed, but to what extent we can go down, and still can we avoid this? Even at low depth of cut, low feed, avoiding this is difficult. And when specification, what is component? What we require is size accuracy, shape accuracy in terms of geometrical accuracies, size accuracies in terms of stringent dimensional tolerances, then surface finish. So these things are to be achieved. Okay. Then only the utility or economic value of the component will be high. So that gives the motivation for our work. Now, traditionally, what are the methods that are being followed for machining brittle materials? So, normally, abrasive methods are taken. So, in abrasive methods, we have grinding, honing, lapping, and polishing. This is loose abrasive processes. Then ultrasonic machining, but this is basically vibration assisted machining. Then liquid abrasive jet cutting. Then non-abrasive methods we have like unconventional machining processes, electro discharge machining, laser beam cutting, electron beam and ion beam cutting. Then friction cutting, microwave cutting. Then this is the what our interest ductile regime machining. So this is a non-abrasive method. Normally this is similar to normal machining, macro machining. Only thing is that controlled depth of cut and feed speed. Then there is a combined abrasive and non-abrasive machining processes are there. Okay, we can say them as hybrid machining processes. So this list is not exhaustive. In fact, all these lists are not exhaustive. You can add many more processes for this. Now, in these, what are the basic problems so that we go for this? In all these processes, what are listed here, basically these processes, grinding, honing, etc. In all these cases, whether it is edge grinding, finishing, lapping, polishing, in all these process, we encounter some micro cracks and subsurface damage in the final output. Though we remove material, but the component obtained, the surface obtained will have some micro cracks and subsurface damages, which is not very desirable. So there is always a need to avoid this. So in that process, what this gives an alternative method. This ductile regime machining method is an alternative method for machining brittle materials to obtain. So we have to avoid that. So crack free surface finish by a ductile and plastic material removal process. So if we go for this, so brittle material machining in ductile regime, so we may end up with crack-free surface finish. So that is the desirable output. So crack-free high-quality surfaces. Okay, and we should develop some. Till now these ceramics, it is a challenge to give
হ্যাঁ
shape to
পাঠিয়ে
them.
দিচ্ছি, পাঠিয়ে দিচ্ছি। হুম, হ্যাঁ হ্যাঁ ওই ওয়ার্ড ফাইলটা পাঠিয়ে দিচ্ছি, ঠিক আছে। হ্যাঁ। আচ্ছা রাখুন, আমার নেটওয়ার্ক কেটে যাচ্ছে, পাঠিয়ে দিচ্ছি।
So machining brittle materials regardless of their hardness and brittleness. So this is some feasibility or enhancement of feasibility. Then another economic aspect, cheaper and higher productivity than polishing processes. Actually, whenever bulk machining is not possible, what we go for is grinding or some polishing process through loose abrasives to try to remove certain material. In these cases, the material removal rates are very small. So we need to increase the material removal rates and achieve higher productivity. Thereby, we may go end up and with cheaper products. Okay. Now, how this is possible for a brittle material? So there is the main window which makes it feasible is normally all brittle materials now they have a small deformation during machining. So this can be highlighted through stress strain curve. Brittle material is characterized by sudden failure without having deformation. But when we say without having deformation, that is not zero deformation. There is small element of deformation is there. Okay. And if the result shear stress at any point of the material exceeds the critical value of elastic yield stress, so the mechanism of deformation transforms from elastic stretching to energy dissipation by means of material removal. So through this, what we can achieve is macroscopic fracture propagation, micro crack formation, phase transformation, dislocations in crystals, intermolecular sliding in amorphous materials. So these things actually give a window of opportunity to have some deformations in the machining, deformations, and we can explore that for machining. So the energy dissipated, that is what when we say the material is machining of brittle materials, so the total energy in that second or third slide when I have shown you brittle mechanism of brittle material machining. So in that actually the total energy which is consumed to have that small chip, in that a small fraction of energy is dissipated or used in ductile regime machining due to plastic deformation. And then the bulk of the material is removed through brittle fracture. Okay, so both are happening, and one is taking place along the slip plane, and another one is cleavage plane through that propagation of the microcrack. So this gives further information. So which is related to size effect. Size effect is non-linear increase in energy consumption when we reduce the depth of cut. Okay. So how that affects this process? So when we have the depth of cut very low, then the total energy is dissipated through plastic deformation. And when we have the depth of cut more than this depth of cut large value, then uh, there will be some cleavage planes which can be generated in that. So in this, the we need to find out that depth of cut below which these cracks will not get formed. Okay. So here the main issue is that the uncut chip thickness greatly affects the chip removal process in the brittle to ductile transition. So in fact, first preliminary phase is ductile phase. Then when you further increase the depth of cut, what we have is brittle phase. So we need to have the uncut chip thickness in such a way that these cleavage planes are avoided. So this a publication of Nakasuji in 1990, they have actually given some inputs for these activities. So in fact, actually, in case of slot milling, we know that the chip thickness is not uniform. It varies from 0 to maximum. In case of slot milling, whether it is even end milling, down milling, up milling, in all these cases, the chip thickness is not uniform. So when we have non-uniform chip thickness, so some part is the uncut chip thickness is less than what is required for material removal. In this case, when this condition is satisfied, there will be only rubbing action, no chip will be removed. Then the ductile mode is achieved just after this, and within a short range till the machining goes to brittle zone. Then brittle regime starts when the undeformed chip thickness further increases. Okay. And we go beyond the ductile zone and brittle fracture occurs. You can this is common knowledge, but in the figure you can observe. So here it is 0, here it is maximum. So in this zone where the chip thickness, uncut chip thickness is smaller than some threshold value, here there will not be any chip formation. It will simply rub. That is known as plowing regime. Then in this zone, the chip thickness is more than the plowing zone, but still it is having only plastic deformation and shear, so that is known as ductile regime. Then further increasing, so the chip formation takes place through brittle zone. Okay, so as we know in milling there is a variation of the chip thickness. We have all these three zones, and then we in that case we can, if we can restrict ourselves to this zone only, then we can have the surface produced without having any micro cracks. So this further explains in case of up milling. Okay, so here it is 0 to maximum, So in this zone, no cracks are formed. Okay. And in this zone, the cracks are formed. Okay. And if the radial depth of cut is further increased, okay, then the machine surface will also have the cracks. Okay. So we need to take care of some critical value, uncut chip thickness in some critical value. We have to keep that below that, otherwise brittle fracture will happen. So if we can keep the brittle fracture point far from the level of final machine surface, then feed rate is low, then no brittle fracture will occur and we can avoid these micro cracks on the surface. Surface gets formed, but it is having micro cracks on the surface. So some literature gives some inputs to this. So plastic flow happens more energetically favorable material removal process than fracture at lower depths of cut. If the size of the critical stress field is small due to the small uncut chip thickness, the cleavage can be prevented. Okay. So all these cases, what is the highlighted point is that we need to have control the critical stress field through small uncut chip thickness. Again, another literature reference also gives the same image. Chip formation takes place in ductile manner if the depth of cut is small enough. So these things actually can be checked through scratch tests, indentation tests. Okay. Like normally we do indentation for finding out hardness. So that actually gives a idea about the uh, up to what point the micro cracks are not generated. Okay. So this is what the window from the uh, normal mechanical property of brittle materials when we compare with ductile materials. So there is a small deformation, okay, before yielding and then fracture. So we need to use this zone. If we can keep the stress field such that it is below this, then we can go for the ductile regime machining. And this actually shows the modes of fractures that take place in terms of loading of material. So this mode 1 is opening, so crack propagates, and mode 2 the shearing is taking place, and mode 3 out of plane shearing is taking place. So through these three modes, we can have the shearing. So, so this gives some insight to have different ways of machining processes. Now, gradually, what we need to obtain, and the tendency, the final aim is to obtain crack free surface. For that, actually we need to check when that crack forms. The hardness indentation is the starting point. So when we have different levels of indentation, normally there is a plastic zone. When you further increase, radial cracks are there. Okay, and these cracks can be of these five varieties. Okay, so the way it may propagate in different ways inside the material, and what we need to find out is that at what depth of cut or what at what critical load the crack is not getting formed. So that is the main essence of further going or further using that information for machining. So load and the length of the crack. Through that, actually, through this experimentation, there is a model developed before now for critical depth of cut. Okay. So through uh, normally indentation is done for hardness test. So based on the shape of the indenter, we have the hardness value calculated, and that can be used to find out the critical stress. Okay, and fracture toughness, we find that in which this is having a zeta value is having given. These are all empirically obtained, and from this actually there is a calculation for model developed for this critical depth of cut, which is related in terms of elasticity of the material, hardness of the material, and fracture toughness of the material. So through elasticity, that is Young's elastic modulus, hardness, fracture toughness, these are all material properties. Through these material properties, we can arrive at the critical depth of cut. Now, this critical depth of cut is a very small value. So these things have been observed in or checked in different processes. One such processes is a uh, ductile regime grinding process. Okay, so in this the based on the machine configuration, stiffness, then other details, the critical value, how small it is, that has to be obtained. So these we are not going into details of these investigations. So in literature they are available. So the basic hypothesis in this, whatever we have discussed, is that regardless of the hardness or brittleness, there is a small element of transition between brittle machining regime to ductile regime. So if we can control that, if we make the grinding in-feed rate small enough, then we can achieve the ductile regime machining. And the main advantage of that is the percentage of surface fracture obtained is very less. So this is, you can see, it's a semi-log graph. So here in this part, there are a lot of surface fractures are there, and in this, when you have a very small grinding in feed, so the percentage surface fracture is less. So that when we say surface fracture is less, that indicates some ductility or ductile behavior of the material is available. So similarly, some other investigations have been done. So in all these cases, the calculated depth, indentation depth is related to the fracture propagation criteria, and through that the critical depth is obtained. And this again, he has done pioneering work in this area. Way back in 1991, he has investigated a lot into ductile regime machining and developed that model, which is famously known as Bifano model, which gives a estimation of critical depth of cut. So we have these parameters. Along with that, some constants are required. Okay. Now, from this work, what we have obtained is there is a possibility of ductile regime machining, and to achieve that, what we require is we want to know the critical depth of cut, and if we can go for uh, machining or critical grinding in-feed rate below that, then we will achieve ductile regime machining. So this first knowing this is important. Then depth of cut below this. Now the issue is this value is very small. Now if the value of this critical depth of cut is very small, then naturally the MRR will be small. So next thought is how can we increase, how to use this, how to determine it experimentally. These two are basic challenges. Then can it be increased further? This is the big question. And in fact, we at IIT VHU had a small attempt to do this. So we have used this knowledge and we tried to increase it further. So the basic idea, it's not very big idea. We know that when we increase the temperature of any material, its ductile behavior range increases. Okay. So that we want to investigate into that. And it has been done by other researchers in different ways. And to determine that the value of this DC, we have used scratch tests of brittle materials as well. Indentation test, then scratch test, and in the scratch, the width of the scratch, depth of the scratch gives estimation of the DC depth critical, or it is also in a way gives the threshold value brittle ductile transition. Okay, so these nano scratch techniques are important. And then indentation technique is another technique which I have this one Vicker indentation technique. So in this actually, so this is what we generally have. Normally, what we expect in a hardness test is we have this impression on the specimen, and then we have those diagonals measured. What we don't want is these things. These are not required. So these are basically cracks. That means the load is more than the threshold value. And so with that, whatever depth we got is more than the threshold value. So when we do this in a controlled way, it gives us the uh, transition, brittle ductile transition. So the formula gives an basis and then it can be found through experiments through indentation tests or scratch tests. So nano indentation is also because these are brittle materials. These values are so small that we need to go for very small loads. You can imagine here 1.96 Newton is the load. It's a very small load actually. So in this, as I told you, these median cracks are to be avoided. So gradually, when we increase the load, those cracks are found obtained. So at the different loads, these tests are performed, and from there we get uh, these values. Okay, so here you can see. So when we have load, this is a gradual increasing load. This is what this test in details. So that is what is the test here. So here it shows a scratch test in which the normal load is gradually increased. Okay. So between 0 to 26, you can see that the surface is totally smooth, no scratch is shown. Then scratch is getting formed, but there are no lateral cracks. Then in stage 3, you have lot of lateral cracks. Okay. So from this, we can find out a different, just the transition phase where the formation of lateral cracks uh, are duct transition. Initially, it is ductile mode. Then, when the load is further increased, it goes to brittle. So from there, we find out the critical depth information and the fracture toughness at that load. So this is what that scratch depth as a function of the normal load and scratch distance. So we are increasing the normal load. So after certain duration, we are getting the uh, the transition, and then because of that micro crack formation, lot of vibrations are happening. And then another important aspect is the coefficient of friction versus scratch distance. This test, it shows that the coefficient friction also gradually increasing. There is a continuous increase in the friction coefficient with increasing load. Okay. So because of this makes increasing ploughing of the sample by the tip with increasing normal load. Okay. And then when the uh, ductile and brittle transition happens, then there are a lot of uh, cracks are happening, and that makes the scratch depth also fluctuate. So through all these experimentation for different materials, this DC is found, critical indentation depth. Okay. So it's being done continuously. So from those things, as I already mentioned, Bifano formulated this. In that, this constant is material specific. So that has to be obtained through experimentation only. Okay, the experimentations may be grinding test or indentation test or scratch test. So these are different tests to get the critical depth of cut. I think we will continue without a break, or you want a break?
It's up to
We can,
you whether if you want to continue.
we can continue because
Okay, if you
break
want to take a
means
break, then
flow will be broken.
okay, then you can continue. No issue.
Okay. So in this, the basic what we have till now seen is either we can go for indentation test, scratch test, or some machining test or controlled machining, which is grinding can be taken as a test. Okay. So from there, we need to find out this constant, empirical constant of the formula, and we will get this. Now, next question comes how to increase that. Before going into that, so there are some figures which indicates the values. Okay, so in this you can see the high speed end milling of soda lime using tungsten carbide tool inserts to accomplish ductile regime machining. In this, the tool used is uncoated tungsten carbide insert, and spindle speed is 30,000 to 50,000 rpm. And what is critical is that you can see here the depth of cut is 3 to 7 micrometer. It's a very small value, 3 to 7 micrometer. If the machine is not a very precise machine, it will not touch half the time, it will not touch the surface. Okay. So this level of values are required for this kind of machining, ductile regime machining. And then feed rate 5 to 15 per minute. So this looks like a big value, but if you see 30,000, so 5 by 30,000, if you take, that will be the per revolution. That is the feed value. Okay. So it is almost 10 to the power minus 4 near of that order. So it's a small value. 10 to the power minus 4 per revolution means it is uh, almost zero point 0.1 micrometer. Okay, so these values actually give an idea about the challenge. That means we are having to deal with very small depth of cut and very small feed. Okay, so that actually motivates to increase it. However, if we can go for this, you can see the surface roughness generated is very low with a minimum of 0.08 micrometer. If you go for, suppose this is the RA value, RA 0.08 is very good. It is basically 80 nanometer. Normally, in case of normal precision machining, if you go for turning or any, it is around zero point 0.5 micrometer. 1 micrometer, zero point 0.5 micrometer is considered as a very good roughness achieved for macro machining. Okay, so less than that is obtained. That means the glass surface generated is quite smooth. Okay. But if we have these parameters as the depth of cut and feed, the material removal rate will be very low. Okay. So this is the schematic diagram for that test high speed the high speed and milling. High speed in the sense the actual cutting velocities are not very high, but the RPM is very high. Okay, 30 to 50,000 RPM. So those are actually common in micro machining. Micro machining, we have even nowadays up to 1 lakh, 1.2 lakh RPM is already being used. So we'll skip some part of this so that we'll go for other details. So these are actually some details of the experimentation, how they have arrived at the conclusions. So through these, what they have achieved is the surface integrity was good and no subsurface cracks or fractures were obtained, and surface roughness generated was very low with minimum value is 0.08 micrometer at this cutting speed and zero point 0.5 micro tool diameter. So this is basically 500 micrometer and milling and mill. So it is possible to cut soda lime glass in ductile regime machining at these conditions. This is what the conclusions of these experimentation. Okay. With normal uncoated tungsten carbide cutting inserts. And then further, as I already mentioned, there is a motivation to increase this critical depth of cut. So in that direction, there are some experimentation has been done, temperature versus hardness of the glass. So when the hardness is that is checked by using different loads at different temperatures. Okay. So it is actually not very big intelligence is used. It is just if you are increasing the load and if you are increasing the temperature with these combinations, when the crack forms. So after indentation, we check it through uh, optical micrographs. So it shows whether these median cracks are formed or not. So at what load and at what temperature they are not formed. That gives the information about the critical. So with when you increase the load, crack length increases. Okay, that is of course quite obvious. And with increasing temperature
Tuk-tuk.
at different loads, the crack length growth is less. Okay. So from these details, actually, from these experiments, extensive experimentation, they uh, these are the conclusions, which are of course obvious, but only thing is that we need to find out what is the nature of the change, at what rate the hardness is decreasing as the temperature is increased. So in this range, through these Vickers indentation experiments, that it has been observed that the hardness decreases as the temperature increased. So this, and in that the radial crack length measured at the surface increased with temperature due to increase in So these experiments give an idea that if we can increase the temperature of the specimen, then there is a possibility, because E by H ratio is important for the DC. In that Bifano model, we have one term which is E by H. So if H reduces, this DC will increase. So that is the effort. So now uh, at the same time, E should not reduce too much. If H is reducing, E is also will reduce to some extent, but both should not reduce at the same rate. So what we should finally end up with higher E by H. So to with these inputs, people have tried laser assisted machining. This is also a well known domain. People to increase material removal rates to improve the surface roughness, people have adopted this, which can be extended to brittle materials as well. Okay. So in that local heating, in this process, what happens through this laser heating source, the small area in front of the tool is heated. Okay. So because of that reduction in hardness, the material removal becomes easier. Okay. So in this process, of course, we have some heat affected zone. After the machining is over, some heat treatment can be done to improve the material properties. But there are certain problems with this as well. Okay. So these are certain characteristics of laser assisted machining. So these are the parameters: laser beam power intensity, spot size, beam distribution, and scanning velocity. Based on this, the localized laser effects matter. Okay. So in that actually the major effect is this one, thermal stress gradients. When we are locally heating the material, so material softens at a very small domain and other part is not getting heated up. So there are large thermal stress gradients come into picture. And because of that, local yielding, loss of stiffness, thermal cracking, and local buckling may occur. So these are actually negative effects of local heating. Though it is assisting the material in machining, so these uh, processes have certain inherent difficulties in them. So thermal stress because of temperature gradients, we have thermal stress also coming into picture. Okay. And in that actually, when we are increasing the temperature locally, then when we have high, you know that lasers have capability, if you reduce the spot size to a small one, the material can even evaporate. Even, so that is how the laser machining takes place. Ablation takes place. So in this case also, if the laser power intensity is not controlled properly, there is a possibility of phase change, okay, which may result in material melting and evaporation. Then in between, there may be some other effect, physico-chemical interactions or physico-chemical effects can be there. Okay. So keeping these however, they increase the process efficiency of the materials which are difficult to cut when compared to conventional methods. These are these LAM methods are now established methods. In some materials, which are known as difficult to cut materials, laser assisted materials, laser assisted turning, milling, drilling, grinding, etc., have been undertaken. How, However, there are some issues, as we have pointed out. Local heating creates the non-uniform heat affected zone, then these high thermal stresses, and this is if you are using single point cutting tool, so the area in front of the tool may be heated in a better way. But so with these issues in mind, what we have thought is, let us try with bulk heating. So in case of bulk heating, so the total material property is temperature is getting increased, and the thermal gradient is very less. So when the thermal temperature gradient is less, the thermal stresses will be minimum. So this may be suitable for all machining processes. So this shows the uniformity in heating. In this case, the central part is heated to large extent, then gradually the temperatures are less. So this gives the main motivation or research interest that the heating of ceramic samples can lead to better ductility so as to better machinability. So here this gives some idea about increasing the critical depth of cut. There is a possibility. Then bulk heating of the samples can be better option than localized heating by means of laser sources to reduce the thermal gradients. Then with this idea, we need to check the through machining work on glasses subject which are mostly subjected to grinding and polishing, which are very slow processes. So if this machining process is successful, so we can go for glass machining instead of grinding and polishing, which is being done nowadays. So with that in mind, we have chosen that bioglass as the candidate material for some investigations. So this is a new approach, this elevated temperature with bulk heating. So that is what some effort has been put at IIT BHU. In that, one PhD scholar has worked actually in this area, and so in that the uh, before going into that, some little bit information about the sample preparation of bioglass. So this is actually indicates the material composition which are taken, and to keep all the specimen of uniform composition, at once the total material is prepared, so it goes through this mixing of the powders. Then it is divided into some batch size, okay, and kept in alumina crucible, then charged in high temperature electric furnace, and it is held at this 1400 degrees centigrade for 2 hours. So after with this the glass, we obtain the glass, and that molten glass has to be cast into plates. Okay, so it through some molding it is cast. So through this glass specimen have been prepared, and which will be used for different experimentation. So these are some details of the glass formation and how the glass property can be changed through annealing. So, as I told, the bulk heating and then doing some experiments to obtain the critical depth. So, a portable heating setup has been developed. Okay. Then, using that heating setup, that heating setup is loaded to scratch tester on which the specimen is mounted. Then the effect of the traction force and scratch speed at different temperatures are checked. Okay. And from there we found the brittle ductile transition and critical depth of cut. Further then optimization of that we have done. So I will give some idea about these things. So it's a small portable heating setup. Some parts are shown here. So this is the actually heating setup. Okay. So it is basically is having a heating coil. On that the plate is mounted, steel plate is mounted on which the specimen, ceramic specimen or bioglass specimen can be mounted here. And so below this plate the heating element is there, and then to maintain the temperature constant on this specimen, there is a water jacket. This is a double walled housing, so in that there is a water jacket, so water can be flown in that to maintain the temperature constant. And then to obtain different temperatures, the heating rate is controlled through using a variac. So we can control the power supply through the variac, and from there we obtain. So these things are carefully designed, and the characteristics of the heating elements are obtained. Then that is mounted on this, and then the scratch testing is done, and from there we get the uh, through the load sensor we get the load variation. Okay, that in fact we take ramp loading. Basically we gradually increase the loading, and we check the characteristics through the acoustic emission signal. So through that we find out what is the, it is acoustic emission is actually one signal which is basically the vibrations generated through the elastic emission of whenever some material is undergoing some deformations, it emits some elastic waves. So that is captured through this acoustic emission sensor. So this is the actual setup. This is the variac kept here. So this is the scratch tester, and here the specimen is mounted, and the data is recorded in the computer. This gives another view. So in this specimen, some coolant is flown. Basically, water is flown through that to keep the temperature uniform. The different experimental conditions it is shown. So we need not go into it. So some details about the heating setup. So that is developed to uh, increase the temperature up to 426 degrees centigrade. Okay. So the heating setup can hold the uh, specimen at the same time it can heat, and it can be used with any machine. Any machine means you can load that to any work table of the machine, and you can use it either in indentation or scratch head or some VMC surface grinder. So it is a multi-purpose. Some elements of details of that heating setup is shown here. This slide gives you the details. So this is the top plate, and here the heating element is put, and this housing is a double walled housing, so having some thickness, so the coolant can enter one side and it can come outside, and this is the vise which is holding this. And we are having a voltage regulation through this variac. Okay. So this is what a small device, but carefully designed and developed, and to satisfy the characteristics. It is not putting any heating element, and if somebody looks at it very superficially, it gives that kind of impression. And then this is characterized through some tests, so heating tests. So at different voltages, what is the temperatures obtained? Those things are characterized, and through that, so we got these characteristics at different currents. So what is the uh, with time, how it is varying, and then current versus temperature obtained. So here the maximum obtained is somewhere here, that is 426 degrees. Okay, and it is giving a mostly linear curve. Okay, and the average heat plate temperature is little more than this is specimen sample temperature. This is heat plate temperature. So that is about the heating setup, and using that heating setup, the influence of traction force and scratch feed is done through micro scratch testing. So here these are the variations in the temperature. 27 is basically room temperature, and the load is ramp loading, that is gradually increasing load, and that loading rate increase is this one, zero point 0.2 Newton per mm. So as the scratch tester indenter moves, so for every 1 mm movement, there is an increase of uh, 0.2 Newton in the load. Okay, and the scratch speed is varied. This one plus 1 mm gap is there. Okay, so with that, so we choose different starting load. So there are certain experiments have been done with these operating parameters, and these are the details. Through that scratch, the scratch, every condition, some 8 scratches are done. So then the scratches are numbered. So then in some cases, at different loads, different temperatures, what is the scratch depth, those things are studied, and how the force variation is taking place at different traction force and at different instances. So we try to evaluate those things, and also the SCM images. Here actually there is some limitation to obtain the SCM images. This is actually, the specimen is bioglass actually. So there is a problem with looking at that through optical method or SCM. In both the cases, taking images is difficult. So we need to have some coating, and then we can see the lateral cracks. So through all these, actually, we can arrive at this is what at different loads, at different temperatures, different scratch speeds. We conducted the experiments, and then through that, actually, I will show you one more graph. These details. This is one schematic diagram. So when the uh, scratch is going on with different loads at different temperatures, gradually the scratch width and depth is increasing, and there is a point where the ductile brittle transition is there. After that, the micro cracks or lateral cracks are more visible. So this point is demarcated. This gives the point of critical depth. So, and how that critical depth is increasing when we have elevated temperature. That was the main point of study, and that is how it is obtained at different places. The width is actually evaluated along this section, and from there the depth is obtained. Okay. So at different cracks, and same thing is repeated for different conditions, and for every condition the critical depth is found, and that gives an idea of the critical depth with reference to the temperature. And using this, so with temperature we know that the hardness and elasticity of the material changes. So there was an effort to highlight that and again to model or to modify the Bifano model through some empirical constants. Those things I don't want to share further, but so this is how the small idea of bulk heating has been implemented, and there is an effort to increase the machinability of brittle materials. Increase the machinability in the sense to increase MRR. The aim is to increase MRR without lateral cracks, without the cracks. So this is the aim, and if this can be achieved, then routinely brittle materials can be machined. Please understand that now they are not routinely machined. At best, some grinding is done for fabrication work. So there are some more details are there, but I would like to conclude my talk here. And if any questions are there, I will gladly take that and try to answer the queries. Thank you very much for patient hearing.
Yes, it was a wonderful presentation on conventional machining. So nowadays, with the importance of non-conventional machining, so the conventional machining has been kept in the sideline. But still, I believe that conventional machining plays a significant role in mass production system till now.
Yes, MRR matters actually. MRR and
Yes,
economy,
yes, yes, yes,
economic
yes,
feasibility,
yes,
that matters.
exactly. So, however, we go for this non-traditional machining and additive manufacturing, but the conventional machining in the CNC mode, it's still predominating the entire industry market. Okay, so this work is really an outstanding example for the researcher who can venture out in the conventional machining part. Now, one query, if anybody is not asking, I'll be putting in this way. Like in the high speed machining, you have said like it's more than 50,000 RPM. So, however, the cooling part.
Actually, the RPM is 50,000, but the actual cutting velocity in terms of peripheral velocity, it will be just 50 or 60 meters per minute, because the cutting tool diameter is just 500 micrometer, zero point 0.5 micron. So
Okay.
if we take that pi dn by 60
Mm-hmm.
to find out the meters per minute. Meters per minute is not very high value. That is
Okay.
one aspect. Another thing is that the cooling part is always taken care through some MQL. Actually, people are trying to put some lubrication in the tool workpiece zone through mist cooling or some
Exactly.
MQL lubrication.
Yes. Mist cooling is one of the favored technique nowadays which
Yes,
are
yes,
being
yes.
used
Mist cooling is
in, yes,
because
in
it's
high speed
environmental.
machining. Yes, it increases the surface area of the coolant through mist cooling,
Yes, yes, yes.
and that significantly reduces the temperature as well as protects the tool life significantly. So, like when we are using this micro machining, are we going for brittle tool materials?
Yes, yes. Normally, actually, tool materials are brittle. Normally, because
Mm.
HSS is not so brittle. HSS is having ductility. But
Ductility, right?
nowadays, we don't use HSS too much. We
CBN,
start with cemented carbide. Cemented
cemented carbon.
carbides are hard and brittle material.
Right,
Then ceramics, then because for tool materials we want a higher hardness. With
right, right.
higher hardness, the brittleness also comes. That's why actually they are used as inserts.
Yes, they are
We
inserts.
have
They are inserts. Because of the cost factor, they are made. They have made
yes,
inserts.
yes, yes,
And nowadays, with the vapor deposition technique, also the contact point of the tool is also getting
yes.
modified.
Coated tools are coming.
Coated tools with
Coated
vapor
tools.
depositions.
They
Coated
are
tools.
again hard coatings only.
Right, right.
Nitride coating,
Right,
cyanide coating,
right.
uh,
It also changes the responses to a great extent.
friction characteristics, tribology
Exactly, that
characteristics.
to a great extent. So these are the new developments which are taking place. I mean, the metallurgists are working day in and day out to find out a better solution for economic machining in this way, or the machinability to be more effective rather. So, any questions in this regard? Anybody? Now, this brittle material machining is really a challenge. In conventional mode, it is really a challenge. Now,
Yes, people are going for this indentation scratch only. It is actual machining is yet to be done.
yeah, but with the help of non-traditional machining like ultrasonic vibration, USM, ultrasonic machining,
That
uh,
is there. That is
yes,
there. But
uh,
again, they are all energy intensive processes.
right, right. Ultrasonic vibration assisted machining as well as abrasive jet machining. These are the machinings which are very effective on brittle materials like glass and ceramic materials. And people, and nowadays this water jet machining has come up to a very large extent. Water jet machining, it can be used on any brittle materials, be it glass, be it ceramic, marble, and if abrasive particles are mixed with the water jet, so the cutting effectiveness also increases to great extent. And also, since there is no cutting tool involved, so it's a green cutting technology, water jet cutting.
Yes, yes, yes.
So I have seen this water jet cutting in CMERI as well as in Jadavpur University.
Yes, that I think
Yes,
Vijay Bhattacharya sir,
yes, yes,
he was
yes, yes,
doing
yes,
this.
yes, 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 yes.
At IIT Madras also abrasive water jet cutting, the
They have,
abrasive water jet cutting.
right, 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 right. Yes, abrasive mixed with water jet.
Ah, yes, yes.
Yes, yes. In Glass Ceramic Research Institute, CGCRI, Glass Ceramic Research Institute in Jadavpur, they have a very good water jet cutting equipment. Okay, I had that opportunity to visit their lab. So they have developed it, and they are using on cutting glasses and ceramics to a very large extent. They are developing new ceramics, and they have also used this water jet technology in cutting those ceramics. So it is very effective nowadays. So all in all, it was a wonderful presentation, and I hope the participants have enjoyed and learned a lot from the fundamentals of metal cutting. Okay, so this is a very traditional subject, fundamentals of metal cutting, both ductile and brittle materials, how they are machined. Okay, the technology in machining has been well explained by Professor Rao. It was a wonderful deliberation, and very fundamental information has been portrayed through his deliberation. It was very nice to hear. So we are at the end of this session. So I'd like to thank AICTE and their permission for ATAL FDP. They have granted us. We are really grateful to AICTE for providing us this opportunity to host faculty development program under the banner of ATAL FDP, and our institute, Haldia Institute of Technology, the entire management of Haldia Institute of Technology has been very much helpful in helping us out with all the logistics and support. All the members of mechanical engineering department, my co-coordinator, Professor Dr. Abhishek Samanto, then we have Shirup Banerjee, Dr. Shirup Banerjee, then we have Pritam Pine and all the members of mechanical department, Saurabh Patnaik. They have worked really hard to make this event a very successful one. All the participants from academics and industry who have joined, and the entire week has been very much eventful. I hope with the spectrum of all the parties, all the experts they have deliberated, I hope it was very enriching in gaining knowledge as well as venturing in out for doing their higher research works. It was really nice to hear from so many personalities of diverse field of engineering. So all in all, this week ends, this online mode of FDP ends today. So from Monday onwards, we'll be having the physical mode of faculty development program, where the faculty members as well as the participants from industry will be visiting our institute, and they will be having the physical mode of faculty development program. Okay, thank you, Professor Rao. It was wonderful to hear from you after a
Thank
long
you very
time.
much
After a
for
long time.
giving this opportunity.
Right, right. It was really nice to hear from you with all the fundamental informations. and lecture was fantastic. Thank you. I hope we can again contact you for
Yeah,
further
definitely.
assistance and advices. Okay.
Definitely.
Okay.
Okay,
Wish
thank you. Thank you everybody.
good night. Good night to everybody. Thank you.
Thank you.
Good
So I
night, sir.
can leave now.
Yes. Thank you, sir. Thank you. Thank you.
Thank
Good
you.
night, sir. Okay. All the participants are hereby informed that they should complete the MCQ which has been given to them. So this is for this week's assignment. So they should complete and submit today. Abhishek, you want to say something, please?
No, they should give the same thing I want to say. That is, they should give the feedback from also the MCQ given in the Google form within today,
Right,
so that we can complete this week's schedule. And from Monday
right,
onwards, our physical mode will start.
right. So I'll expect all the participants to be present on Monday so that we can have a offline mode of faculty development program. All in all, it was really good. Participation was also encouraging. So we end today and this week of online mode of faculty development program. Good night.
Yes, sir. Good night. Thank you to all the participants also for